In this video, we're going to look at one of the most fundamental concepts in optical spectroscopy, transmittance, and how it connects to absorbance and the Beer-Lambert law. When we shine light onto a sample, like in UV-Vis spectroscopy, the light coming from the source has an initial power, which we call P0. This beam enters the sample, usually held in transparent cuvette. As the light passes through, some of it interacts with the molecules in the sample. Depending on the chemical species present, the sample may absorb some wavelengths of light and it may scatter some small fraction as well. What's left? The part of the light that successfully makes it through reaches the detector and has a power of P. The ratio of these two, T is equal to P over P naught, is called transmittance. Transmittance tells us how much light passed through the sample. A transmittance of 1 or 100% means the sample did not absorb any of the wavelengths. It's completely transparent. A transmittance of 0 means all of the light was absorbed before reaching the detector. While transmittance is a simple idea, it becomes incredibly powerful when we transform it into absorbance, and it's defined as A is equal to negative log of T. Absorbance is preferred in quantitative analysis because it has a direct linear relationship with concentration, and it's described by the Beer-Lambert law. A is equal to epsilon times B times C. Here, epsilon is the molar absorptivity, which tells us how strongly the molecule absorbs light at a given wavelength. B is the path length, the distance the light travels through the sample, and C is the concentration of the sample. This equation is a cornerstone of UV-Vis quantification. Now, the reason this law is so valuable, especially in analytical chemistry, is because it produces a linear plot. When absorbance is plotted against concentration, you get a straight line as long as they behave ideally. This linearity is extremely important. It means the sensitivity, or also known as slope of that line, and it stays constant across the working range. In other words, this instrument responds consistently to change in concentration, making calibration straightforward and reliable. Linear plot allows us to detect small differences in concentration and gives us confidence that our measurements are accurate and predictable. So when we talk about transmittance, absorbance, and the Beer-Lambert law, we're not just describing the light passing through a solution, we're laying a foundation for precise quantitative chemical analysis. Understanding this relationship is essential for anyone working with optical techniques, from academic labs to pharmaceutical analysis and beyond.